The first law of thermodynamics. Thermodynamic laws are kind of depressing. So another way we state this one is there is no free lunch. So think about it. Some of the local schools here have free lunch, right? All the kids of the school can get lunch for free. Is that lunch really free? No, the taxpayers are paying for that lunch, right? It's not free. First law of thermodynamics, there's no free lunch. What that means is that the energy has to come from somewhere, right? The money for the lunch came from somewhere. So thermodynamics, we're studying energy, thermal, and the interconversions, dynamics, the movements of it. So the total amount of energy in the universe is constant. That's the first law of thermodynamics. You can never design a system that will continue to produce energy without a source of energy. You can't get something for nothing. Back in the 1800s, maybe even the early 1900s, there were a lot of con men who were, maybe they believed it was true, but they had these perpetual motion machines, right? They'd make this thing that would just keep moving, keep giving off kinetic energy without being fueled by something, right? So turns out that that's not possible. All of those things that appear to be you're getting motion and kinetic energy for nothing, turns out there was a hidden source of energy. So you can't get something for nothing. And we need to talk about state functions. So let's look at elevation here. So here we've got a mountain, and there's two different paths up this mountain. There's path A, which is not as steep. You're ending up with a lot of switchbacks going back and forth and back and forth. And to get to the top of the mountain, you're going to walk 12 miles. There's another path that basically goes straight up the side of the mountain. It's going to be a lot harder to climb, but it's shorter. It's only 5 miles. The elevation at the bottom of this mountain is 0. It's at sea level. The elevation at the top of the mountain is 10,000 feet. Your change in elevation when you go from the base of this mountain to the top of the mountain does not depend on how you got there. If you took path A, you still experience a 10,000 foot elevation change. If you took path B, you still have a 10,000 foot elevation change. My favorite way would be to get in a helicopter down here and go up in the helicopter, fly over here, and then be lowered down onto the top of the mountain. But the elevation change is the same. That is a state function. State functions do not depend on how you got from point A to point B. It's just the difference. Okay? So the distance traveled in path A or path B or taking the helicopter is going to be different, but the elevation change is the same. Any questions? So we can talk about something called the internal energy of a system. So when we talk about internal energy, we're talking about the sum of the kinetic and potential energies of everything in that system. So if we're looking at the hand warmer, we're going to look at all the kinetic and potential energies of the iron filings in there, the package itself, and all of those things, the total amount of energy. Internal energy is a state function. It depends only on the state of the system right now and not how it got to that state. So if we look at change in internal energy, which is like change in elevation, the change in energy is just the difference between the final and the initial amounts of energy, just like the change in elevation is the final elevation minus your initial elevation. So this triangle here is the Greek letter delta. And we use that pretty uniformly in science to mean the change in. And we're always talking about the final value minus the initial value. Because the change can be positive or negative. So it's always, where are you now? Subtract where you came from. In chemical systems, the reactants would be the initial state, and the products would be the final state. So here we start with carbon and oxygen, and these are going to react and form carbon dioxide. Well, what's the original internal energy of the reactants? So this is not to scale or anything, but we're expressing internal energy increasing as we go up, which is typical of the y-axis on a graph, right? Up is bigger. So here we have carbon and oxygen, and their original state, their original internal energy is up here. When this reaction occurs and we produce CO2, the CO2 has a lower internal energy. The sum of its kinetic and potential energies is less than carbon and oxygen. So it went from high energy to low energy. That means that energy came out of the system. The system lost energy. Where does that go? It goes into the surroundings, right? So if I had, instead of the $10 bill I was talking about earlier, so let's say I had 10 $1 bills, and I lose them, right? They leave me, the system, maybe I throw them into the air. Yeah, let's do that one instead of throwing your keys, right? Where do those dollar bills go? Well, some of them might be caught by people that are standing close to me. Some of them might just lay on the floor or get blown away by the wind or something. But they're not in my possession anymore. They're in possession of the surroundings. The surroundings is everything that's not me. Okay? So if I don't have it, it goes into everything that's not me. So our system lost energy. The energy change for the system was negative. But the energy change for the surroundings was positive. The system gained the energy lost. So the surroundings gained the 10 $1 bills that I lost. Does that make sense? So one change is positive, one change is negative, and whether you think it's positive or negative depends on who you are. Right? For me, losing $10 bills is negative, but for the surroundings, for the collective surroundings, it's positive. Right? Might be 10 different people around that get $1 each. Well, they each got $1. Total, that's positive 10 to my negative 10. That make sense? When you throw dollar bills in the air, new ones don't appear, right? You don't suddenly end up with 15. And they don't disappear either. Maybe you feel like you lost one, but later you find it under the couch, right? They don't just disappear into thin air. So this is what we call an energy diagram. And this shows us the energy change that occurs during reaction. You can think of it like an altitude diagram for climbing a mountain. So here, the people hiking started out at a high elevation and went to a lower elevation. So their elevation change was negative. They went down. Well, the opposite can happen as well. Here we have the same what am I looking at here? Oh yeah, I'm jumping ahead of myself. That's what I thought we were going there. Okay. So here, the reactants have more energy. So energy is lost by the system. Energy is gained by the surroundings. So the change in energy for each of these is the same number. But for one it's negative, and for the other it's positive. So when we say that delta E surroundings is equal to negative delta E system, that does not mean that this is a negative number or that this is a negative number. It just means that you take whatever the change in the system is, you multiply it by -1, and that's what the other one is. So if we said that x, that doesn't work very well. If we say that x is equal to -y, it's a really simple equation, very easily misunderstood. If y is 5, let's say y is equal to 5, what's x? -5. What if y is -2? What's x? +2. Okay? It's the same number, just the sign is different. So it's like transferring money between accounts or between people. It's positive for one, it's negative to the other. And so I sent some money to someone by Venmo. It shows up on my account as -$20 and on theirs as +$20. What's the amount of money that was exchanged? $20. Well, is it positive or negative? It depends on your point of view, right? So here we have the same chemical chemicals, but the reaction is going in the other direction. So we have carbon dioxide forming carbon and oxygen. Well, the internal energy of carbon and oxygen is the same as it was before. It's higher, and the internal energy of carbon dioxide is lower. Why? Because they have different compositions. They have different their electrons and protons and stuff are arranged differently. So when this reaction goes from CO2 to carbon and oxygen, we're starting at the bottom and going up. And so our system, the chemicals, are gaining energy. Where did that energy come from? It came from outside the system, the rest of the universe, the surroundings. So here, energy went from the surroundings into the system. It could go from the system to the surroundings or from the surroundings to the system. It's the same amount. The sign just depends on which side you're looking at. So again, the energy gained by the system is lost by the surroundings. In this case, delta E surroundings is negative, and so delta E system must be positive. Any questions? So if reactants have a higher internal energy than products, then the change in energy for the system, the reaction, is going to be negative. Energy is going to flow out into the surroundings. If the reactants have a lower potential energy or internal energy than the products, then energy will be flowing into the system. So again, it's like money in your bank account or money in a Venmo account or something. Money leaving is negative, money coming in is positive. So consider these fictitious internal energy gauges that describe the initial conditions for a chemical system and its surroundings. So here we have the chemical system. Its tank is 3/4 full, and the surroundings is 1/4 full. Which of these, A, B, or C, correspond to the final conditions following an energy exchange in which delta E system is negative? So before we look at that, delta E system being negative, so here's the system. Is its energy going to get bigger or smaller? Smaller, because energy is going to come out of it, right? So we're looking for something where this bar gets shorter, and where does that energy go? Into the surroundings, and so this one is going to get bigger. How much bigger? It's the same amount. right? If the chemical system is my Venmo account and it loses $20, the surroundings, which could include more than one person's Venmo account, are going to gain $20, right? Okay, so which of these describes that change? A, B, or C? A. Because in A, we see that the system went from 3/4 to half, and the surroundings went from 1/4 to 1/2. So the chemical system lost a quarter tank, and the surroundings gained a quarter tank. In this example, or this choice, the chemical system lost energy, but the surroundings didn't gain energy. Is that possible? No, because energy cannot be created or destroyed. It has to go somewhere. And, like with money, it may be under the couch cushions or something. Maybe you can't find it right away, but does that mean it doesn't exist anymore? No, it went somewhere. And then what's wrong with this one? Is this a negative change for the chemical system? No, it's positive. It's getting bigger. Okay? Heat and work are means by which energy is exchanged between the system and the surroundings. So we've got our system and our surroundings, and energy can go back and forth, and there are two methods for that. One is heat, and one is work. Heat and work are not state functions, so they do depend on how you get there. But the change in internal energy will equal the sum of the heat plus the work. So delta E can be positive or negative, and Q and W can also be positive or negative. So for delta E, we've already talked about this. A positive change means energy is flowing into the system, like it's positive for me when money comes into my account, right? The numbers go up, it's positive. It's negative when energy goes out of the system. So what are the sign conventions for heat and work? Q will be positive when the system gains thermal energy, and will be negative when it loses thermal energy. So here the heat is energy that's transferred due to a difference in temperature. So if Q is negative, that means thermal energy went out of the system. So that's just like the money. The work one, you have to think about a little bit differently. So work done on the system is positive. Work done by the system is negative. So think about how you feel when someone does work for you. Is that nice? Maybe somebody's giving a massage, they're doing work on you, or they're mowing the lawn for you, they're working for you, right? That's nice, right? How about when you do work for somebody else? Yeah, not as nice, right? So it's negative if I, the system, do work on or for something else. It's positive if the surroundings are working on or for me. Okay? So back to our billiard table here. Looking at that first ball, that lost energy, and the energy that it lost is gained by the surroundings. So how does that happen? Well, initially, let's say this ball had kinetic energy equal to 5 joules. As it rolls across the table, it's going to slow down a little bit, right? Because even the best pool table, there's a little bit of friction, right? And so as the ball rolls, through friction, heat is lost. Just a little bit, half a joule. When it gets over here, the white ball now has 4.5 joules of kinetic energy, which it transfers to the purple bulb by doing work. It's applying a force through a distance onto the purple bulb. So what we have here in terms of the surroundings is that in terms of the system, the white ball. So here, the white ball did work, negative 4.5 joules, and it lost heat, negative 0.5 joules, and so its change is negative 5 joules. At the end here, it's at 0. Where did those 5 joules go? They went into the surroundings. The surroundings could be more than one recipient, right? Because some of it was to heat that went into the table itself, and some of it was kinetic energy that went into the movement of the ball. What if we have an old, abused pool table where the surface is rough, right? Not a very good pool table. And you start out with a cue ball, 5 joules of energy, you send it across. Well, at the end, it ends up with 0 just like it did before. So its change is negative 5 joules. The final is 0 minus the initial of 5. But how that happened is different. Because there's more friction here, this ball lost 3 joules of energy as it rolled across this rough table. The heat lost is Q. So Q is negative 3 joules. By the time it gets over here to connect with the purple ball, it is moving more slowly, right? It only has 2 joules of kinetic energy to transfer to the white ball. So W is minus 2. But the sum of those is still negative 5. The energy lost by the first ball is gained by the surroundings. Any questions? So delta E was the same for the white ball in both cases, but Q and W were not the same. Delta E as a state function depends only on the initial condition and the final condition. Here we're looking at the velocity of the ball before and after. Both cases started with 5, ended with 0. Q plus W is the change in energy. It's the same for both tables, even though the individual values of Q and W were different. Okay, so let's try a problem here. A cylinder and piston assembly, which we're defining as the system, is warmed by an external flame. The contents of the cylinder expand, doing work on the surroundings by pushing the piston outward against an external pressure. If the system absorbs 559 joules of heat and does 488 joules of work during the expansion, what's the value of delta E? Well, the change in internal energy is the sum of the heat plus the work. So what we need to do here is identify the heat and the work with their correct signs and then add them together. So here it says the system absorbs 559 kilojoules of heat. The system is absorbing it. Is that positive or negative? It's positive. My account is absorbing money. This is good, right? This is positive. So that's positive. I'm going to put a plus sign there. It's not necessary, but I'm going to put a plus sign there just to show that we thought about this. It's not just that we wrote a number and didn't think about whether it was positive or negative. What about the work? It tells us the value, right? 488. Oh, I'm sorry, that wasn't kilojoules. It was just joules. 488 joules. The system does work. So you're the system, you're doing work. Does that negative or positive? As negative, because you are expending energy for the benefit of someone else, right? So we've established that W is negative and Q is positive. Questions about how I got those signs? So then to find our answer here, we're going to take our Q, 559 joules, and we're going to add the work. The work happens to be a negative number. And, don't overthink the positives and negatives there. Just type it into your calculator and let it worry about that. So 559 plus negative 488, your calculator can handle that, is 71. So heat was exchanged, work was done. Did the system come out with more energy or less energy after all of this? It came out with more, right? Because this is a positive number. It spent some energy doing work on the surroundings, but it gained more energy and heat than it lost through work. Okay? So sometimes you can make an investment, right? You put your money in the initial investment, and then the payback is greater than your investment. You come out ahead. That's what you hope will happen. But other times you make an investment and you get a payback, but the payback is not as big as your investment, and so you come out losing money. So it could go either way. 71 joules.